going in a slightly different direction, I'm going to talk about our framework for compiling traffic analysis applications. So starting by orienting to the space, over the years, passive traffic analysis has helped researchers, developers, and operators do a lot of very cool things, including discover security vulnerabilities, develop methods to circumvent censorship, learn about the deployment of new protocols, identify and address performance degradation, and so on. And people have been analyzing traffic for meaningfully longer than I have been alive. But today's traffic analysis workloads present increasing challenges. So even mid-sized ISPs and enterprises are seeing hundreds of gigabits per second of traffic. And the questions that we want to ask have increasingly complex semantics. So think reassembly, parsing, and inference, not just net flow packets and logging. And the applications and protocols are becoming more complex and opaque too. So given these demands, what do researchers and operators do today? In general, we have two options. We can either build an experiment-specific system over a packet processing framework like DBDK, or we can try to use an existing tool that may not fully meet our needs. And I'm going to go through both of these options in a bit more detail. And I'm going to start with option one in order to introduce a concrete example. And my goal in walking through this is just to show that you could, but probably would not want to implement this from scratch. So I'm using an example of inferring video resolution from connection features. And this is inspired by a very large and ongoing body of work. At a high level, what do our abstractions look like here? We need to identify video traffic, extract some features, and then pass them through some kind of classifier to get resolution estimates. This is pretty standard, state-of-the-art. And I'm going to expand briefly on the work required for each component of this. First, to filter on application layer data, you need some kind of prefix TCP reassembly and some high-speed bidirectional application layer parsers. For DNS, we need a cache and a cross-connection lookup table, and conditional logic to figure out which parsers and which filtering pipelines and if and how much to reassemble. And you need another filter on relatively complex derived features. To derive those features for some combination of filtering and analysis, you have to stop reassembly and drop down to a different layer of abstraction and then invoke an online classifier. When we actually get to estimating resolution, this is not something you can get once per connection. This is a windowed metric that you have to update in chunks. And you need a lot of infrastructure to make this work. So some initial packet filtering with NIC offload, a scalable flow table with low latency lookups, and so on. And almost everything up on this screen has some amount of gotchas in it. So for example, we all know how to do TCP reassembly and maintain a flow table. But this is high-speed, multi-directional, multiplexed TCP reassembly when you don't control endpoints, which is a huge engineering and even research challenge. So think memory management, handling potentially enormous and very annoying amounts of stateless scanning and backscatter, loss between endpoints and your monitoring point, and so on. And there's something like this for almost every component of this pipeline. And that is just for one experiment. Operators and researchers almost always need to run multiple experiments in parallel with different requirements at the same time. And I really did try to put this on the slide, and I could not figure out how to. And hopefully you can see how this might add up to something that you probably could, but would not want to build from scratch. Packets are really not the right abstraction for a research question or an operational question like this. And researchers in particular are doing this over and over again. So let's look at option two. Where are we at with existing tools? To get there, let's take a step back and think about what we want from a traffic analysis system. And we talked to operators and researchers, and we conducted a literature review of modern traffic analysis research. And we identified 3 categories of needs. So a very high level of flexibility, think about the features in the video example, common connection and session level abstractions. We need things like TLS certificates, not just packets. And really high performance on the types of hardware that enterprises and researchers actually have, and for multiple workloads at the same time. And no existing tool provides all 3. So for example, you can get reassembled data abstractions with reasonably high flexibility, but only at a few gigabits per second, so you lose performance. And as an aside, because you really can't do much analysis online, you end up with massive storage costs and potentially privacy risks from writing a bunch of data to disk. You can get solid performance with tools tuned to specific domains, but you can't actually extract and analyze arbitrary data. Retina, which is work out of our research group, was a step forward, but it fundamentally relied on a single analysis function and a rigid pipeline. So for example, you could get TLS handshakes or DNS transactions, but not both. And as one example, no existing tool can implement this video resolution application without creating a new domain-specific framework. And this is broadly true for modern, complex use cases. And so as a community, we are still coding things up from scratch. And this is where we introduce Iris, which we believe takes a meaningful step forward in addressing these trade-offs. So Iris compiles user code written in a general-purpose programming language into an optimized traffic analysis pipeline. Users express analysis workloads as functions and data structures in Rust. Iris then decomposes these into control flow, so incremental processing steps and incremental filters. Think something like reassemble a connection if it's TCP until the end of the TLS handshake. And then the Iris compiler fuses all of these intermediate representations together to express an arbitrary number of traffic processing pipelines with minimal aggregate work. And Iris then produces a traffic analysis runtime that is tailored to the specific needs of the application. Going back to what we need from a network traffic analysis system. In order to support a lot of different use cases, Iris needs to give developers the flexibility of a general-purpose programming language. It also needs to expose and allow users to compose stream-level types, so not just packets. And it needs to support all of this flexibility while imposing some amount of structure for our compiler to interpret and optimize across any number of analysis tasks. And I'm going to talk about how we do this in two parts. First, Iris's programming model, and then how our compiler leverages that programming model to make this fast and parallel. And I'm going to start with how you use Iris. So first, Iris directly exposes application and connection layer abstractions to a subscription programming interface. This is Rust code. Our goal here is that for common use cases, using Iris is really easy. A subscription is a filter, data types, and a callback. This is pretty standard, and this is one simple example. The filter specifies traffic of interest, so here connections with this SNI. Data types are what formats do I want the data delivered in. Here it's subnet information and a parsed TLS handshake. And the callback is what analysis do I want to perform on this data. Here that's just logging. There are some interesting type rules when you combine these elements together, which I don't have time to get into in this talk. So with 3 lines of code, you can get the output of an application layer parser. You can filter on fields within that parser, and everything else is abstracted away by the framework. And this reflects a common set of use cases, so we wanted to make analysis like this simple. But how useful Iris is for complex analysis really depends on how extensible these components are. So let's think about what it would take to define a subscription to express something like the video inference example. We need these really custom derived features. We need to statefully accumulate estimates at multiple points in a connection. We need a filter that you can't express in a Wireshark-like domain-specific syntax. And we need this analysis to cross traditional OSI layers. And again, this is just one use case. This does not capture all the needs that we identified. Iris makes this possible by allowing developers to define data types, filters, and callbacks in a general-purpose programming language. We use Rust because of the high performance and safety guarantees. To introduce that flexibility, I need to start with how Iris exposes connection data to users. So Iris models connections as layered state machines, where the layers reflect encapsulation. And then we allow users to define data structures and functions that access and manipulate data through these state machines. This gives us transitions with associated data, things like an identified protocol, a parsed header, or new observed packets associated with a particular connection. This is a recursive hierarchical system, so you can handle encapsulation, and you can define custom state abstractions, like if you want features every 10 seconds. So let's take one part of what you might want to do to get video resolution, something like accumulating a count of downloaded bytes for TLS connections. And the things to pay attention to here are the abstractions that we're using and how they map to the connection model. So we're using 2 primitive data types, the identified application layer protocol, this is as a filter, and then the packets and the payload. And we're using this to build this higher level abstraction of downloaded bytes. Another example, this is a custom filter function that uses 5 tuples and TLS handshakes. This might be part of what you'd use to filter for video traffic. When you define this, you've implicitly hooked into the end of application layer header state defined by a TLS parser. And then you can build up and reuse these abstractions in other functions and data structures. So again, this is a hierarchical composable interface. For example, once our custom filter is defined, we can use it in a callback. The other thing to flag here is that when you use Iris, you get a lot of this traffic analysis functionality for free. And this is not just Iris implementing primitives, it's composing those framework primitives together automatically based on the specific needs of the user's subscriptions. So for the video example, which before took all of this infrastructure, using the Iris compiler, we can do this in less than 200 lines of Rust code, which makes my life better. And this leads me into the compiler. So how do we implement this interface and make it scale? At a high level, the compiler relies on the structure imposed by the connection processing model to create a minimal control flow for each subscription, and then it merges them together. I'm going to walk through that in a bit more detail. So here is an excerpt from the state machines, and remember that this is just one layer. We are dropping a lot of complexity here. Each state or state transition is like an LLVM basic block. So it is a node with a single entry and exit point and no internal branching. Each subscription is defined in terms of state machines. So we can very naturally build a map from subscriptions to these processing blocks in the state machines, and then to the things that need to happen within each state. So something like reassembly or invoke a user-defined API. We call these incremental requirements actions. These are just anything that the framework needs to do incrementally to fulfill a subscription. We then take the subscriptions filter and add incremental conditions to these blocks. So say this is a filter on a TLS SNI. We can identify a connection as TLS before parsing the whole handshake, and we only want to actually get features if the SNI matches. And the motivation for these filters is both subscription semantics and runtime performance. So conditioning incremental actions on attributes of a connection means that the runtime pipeline can do exactly what it needs to do for exactly the connections it needs to do it for. So for example, we cannot reassemble every TCP packet on a commodity server at 100 gigabits per second, but in most cases, we don't have to. We accumulate this representation for each state and for each subscription, and that can be 2 subscriptions or 2,000. And these state diagrams can get complicated. But in practice, subscriptions tend to share at least some incremental requirements. So think initial filtering when you need to track a connection, maybe some shared data type, and so on. And we don't want to duplicate all of that work. But by decomposing each subscription into a structured control flow graph, we can identify pretty granular redundancies and eliminate them. There's more in the paper about how we do this, but at a high level, we represent subscriptions using trees, and then we apply techniques from compilers to aggregate and reduce them. And one thing to emphasize here is that Iris's connection model exists both because it is flexible and intuitive for real-world needs, and because it lets us do this. It lets us decompose subscriptions into incremental filters and actions so that the runtime that the compiler executes, so that the runtime that the compiler outputs can execute multiple subscriptions at the same time with minimal aggregate work. So I'm going to move on to a few ways that we evaluate Iris. And the 2 questions to look at here is how it scales with many subscriptions, so how well this compile time optimization works, and is the interface practical for real-world experiments that people are actually doing. So to stress test merging, we ran a benchmark to see how Iris scales with many subscriptions. We ran this on real traffic on Stanford's network, and we used 2 cores to make sure that we were not limited by the amount of available traffic. And our key metric here is how much traffic can our system process without experiencing packet loss. So first, the subscriptions here are similar, and Iris scales by sharing almost all work across them, which is good. Second, we compare Iris to a naive baseline. This implementation is essentially equivalent, but it tracks subscriptions dynamically, and it does not deduplicate or disambiguate incremental blocks of work. And my takeaway from this is just that running multiple subscriptions really does require granular optimization. It just doesn't scale otherwise. As part of evaluating Iris's interface and real-world performance, we replicated the core traffic analysis logic from 3 recent research works in security, anti-censorship, and network operations. And we ran these both independently and together. We picked these because they have really different requirements. So think a lot of application layer parsing, highly custom features, and a very complex, expensive callback. This slide shows the number of cores required to process traffic on Stanford's network with less than 1% loss. When we ran these experiments over an hour, we saw an average of 100 gigabits per second of traffic with spikes up to 120 gigabits per second. And then it also shows the lines of code each required to implement an iris. So for both, lower is better. If we look back at the original works and caveats, these were in different environments and we don't have access to the original artifacts, but we're looking at orders of magnitude here. So think a few gigabits per second using a system based on Zeek versus 100 gigabits per second with just a few cores. We're also able to write a whole lot less data to disk because we can execute more analysis online. We're also estimating an order of magnitude reduction in developer effort compared to homegrown tools and easier reproducibility. So even if you could get similar performance by building your own experiment-specific system over DPDK, we think that leveraging iris is easier. The other thing that this shows is that there is still a lot of work that iris is effectively fusing together here. So in the HTTP example, the subscriptions were pretty similar, but here they're really, really different. They have very different requirements. But iris is still able to identify incremental, granular components of shared data and processing. So I'll just close by saying that iris is online, and we've been really excited to see some researchers and operators start to use it. And we hope that iris can address real use cases that you might have, and if it does not meet your needs, we would love to hear why. Thank you.